In the previous part of this problem, I managed to define the problem and simplify the governing equations for the very special border I had selected. Our border was a border where one border was doing work and its pressure was 350 kilopascal, and the other border was responsible for heat transfer and its temperature was 1200 Kelvin. Now, I try to simplify these equations and calculate different properties between initial and final condition. Now, let's try to do that. And starting with M2 minus M1 um, gives us that mass doesn't change, which um, is very helpful. What I would need later on is V2 minus V1. And from the fact that the mass does not change, I calculate V2 minus V1. V2 minus V1 equals V2 minus V1 divided by M. I have all the values. V2 minus V1 is 0.01, and mass I have already calculated to be 0.042, and therefore V2 minus V1 equals 0.2381 cubic meters per kilogram. Okay, that's what we get from the mass conservation. Let's move to the first law of thermodynamics, and what we do is that we simplify it for unit mass. So it is U2 minus U1 equals Q12 minus W12. Well, since it's perfect gas, the change of internal energy is only a function of temperature. So U2 minus U1, U2 minus U1 equals, I'm just working on this term. I shall later on work on the other two terms. But for the time being, the change of internal energy is only a function of temperature, and the function is CV0 times T2 minus T1. We have calculated all terms. It equals 0.3122 times 800 minus 400, and the outcome for U2 minus U1 would equal 124.88 kilojoule per kilogram. This is how we calculated this term. Okay, this is how we calculated this term. Oh, we know that to calculate heat transfer, the level of heat transfer, the only equation we have in thermodynamics is this equation. So this would be the last term that we could calculate. For work, we have an equation for cylinder piston work, for in fact reversible cylinder piston work. The only work we have to do is to push this piston up. We assume no friction or irreversibility. So work would be W12 equals P times V2 minus V1. And the pressure is, as I mentioned, 350 kilopascal. So that equals 350 times V2 minus V1, which we have already calculated it to be 0.2381, and the outcome for W12 is 83.335 kilojoule per kilogram. Once we have calculated these two terms in the first law of thermodynamics, then we are in a good position to calculate heat transfer. So U2 minus U1, which is 124.88 equals Q12 minus 83.335. And the final outcome, Q12 would be 208.2 kilojoule per kilogram. And that's how we calculate the first law of thermodynamics. As for the second law of thermodynamics, this is the equation we're talking about. And what we shall do for it is to calculate each term of it for the boundary that we have selected and per unit mass. So S2 minus S1, S2 minus S1 equals Q12 over TB plus S gen per unit mass. Now, let's see what each term contains. S2 minus S1, this term, S2 minus S1 equals, for perfect gas, this is the equation we have, Cp0 ln T2 over T1 minus R ln P2 over P1. Since it's a constant pressure process, this term cancels out, and therefore S2 minus S1, these are not capital S, these are S per unit mass, equals Cp0, which is 0.5203 Ln, and the temperature ratio is 2, as we have already calculated it. It's 800 over 400, and therefore S2 minus S1 would equal 0.361 kilojoule per kilogram Kelvin. Okay, now we have calculated this term. We have Q and TB, so we can calculate S gen. 0.361 we inserted in this equation equals heat transfer, and we have already calculated transfer. It was 208.2, and the boundary temperature we have selected to be 1200 Kelvin, so it is 1200 plus S gen divided by M, and therefore S gen divided by M per entropy generated per unit mass would be 0.1875 kilojoule per kilogram Kelvin. This is how we calculate all different terms in the second law of thermodynamics. Finally, we move to the availability equation, which is this equation, and per unit mass, it would be A2 minus A1 equals 1 minus T0 over TB times Q1, 2 minus per unit mass W12 minus P0 times V2 minus V1 minus T0 S gen per unit mass. What we do is that we shall try to calculate all terms. And we are able to calculate all terms in this equation since this is not a new equation, it's just a combination of the first and second laws. So we shall only calculate all terms and check if they would equal. As far as A2 minus A1 is concerned, A2 minus A1 equals U2 minus U1 plus P0 times V2 minus V1 minus T0 times S2 minus S1. This equation just calculates this term. And putting numbers to it, this would equal 124.88, which is U2 minus U1. We already calculated from CB0 T2 minus T1, plus P0, which is 100, plus P0, which is 100 times V2 minus V1. We already know that 0.2381 and minus T0, which is 300 Kelvin times S2 minus S1, which we have already calculated it to be 0.361. And the outcome is 0.39 kilojoule per kilogram. You see, out of 208.2 kilojoule per kilogram of energy that was transferred by heat, only 40.39 of it is stored inside argon as availability. Well, another term which you should calculate in the availability equation is this one. It is 1 minus T0, which is 300, divided by 1200 TB, times heat transferred, which is 208.2. And this term equals 156.15 kilojoule per kilogram. What does it mean? It means that it's true that 208 kilojoules of kilogram of heat is transferred through this boundary, but that's not the availability transfer. Availability transferred through this heat transfer is only 156.15 kilojoule per kilogram. And out of that availability, 156, which is transfer to heat transfer, only 40 is stored in the argon. We shall discuss that pretty shortly. Now, let's calculate this term and see what this term is. This term is work, W12 is work and is transferred just so as availability is 83.335 kilojoule per kilogram. This is the availability transferred with work. This is transferred to this piston and its atmosphere, just surrounding is transferred. Now, this term, what is this term? P0 times V2 minus V1 equals 100 times 0.2381, and that equals 23.81 kilojoule per kilogram. As I said, this is the um, uh, availability that is stored in the atmosphere, which could return should the argon wish to return to its dead state. Now, the final term that we have to calculate is T0, Sgen per m, which is T0 is 300 Kelvin, times Sgen over m, which is 0.1875, and that equals 56.25 kilojoule per kilogram. That's the availability loss in this process. This is irreversibility in the process. Now, how do all these things balance? A2 minus A1, which is 40.39, should equal this term 156.15, which is the availability transfer through heat transfer, minus 83.35, that's the availability lost due to work, plus this term 23.81, that's the availability stored because that's the availability stored in the ambient, and minus T0 strength, which is 56.26. This is the availability lost through irreversibilities calculated, and 40.39 would equal 40.375, which is a good enough check for our calculation. Now, in the next video, I shall show you how, when we define our process, we could calculate our properties. It means that in our equations, we define our left-hand sides and calculated properties for the right-hand side. Now, how we can calculate properties of the left-hand side when we define our process on the right-hand side. Well, thanks for watching, and cheers.